Okay, hi, hello. It's working? Yeah. Hello, welcome to my presentation about Mac Rootkits. It's a pleasure to be my first time in Tokyo, and I hope you enjoyed this presentation. It's okay? Oh, it's on. Yeah. Okay. Who am I? There's a difference between the slides. There are some slides that are different, but don't worry, it's very small details. I have been messing around with Macs since 2007, the time I bought my first Mac. I started breaking copy protections. If you look at my blog, it's the way it's on the first posts. And then I moved around to security and lately malware. Dr. Quinn from Capstone, if you use Capstone library, used to call me a legendary white hat hero. Because the past year I have been working on developing a next generation product for macOS. I just quit that company last month, so I'm not anymore a legendary white hat hero. If you like rootkits, I wrote last year a very long article for Frac about rootkits. It's still up to date. You need to change some things, but it's a very good article. And I'm still writing a book about the same subject. And I have the really bad habit of creating too many slides on my presentation. So please apologize me if this presentation is a bit bumpy, because I have 166 slides and not enough time to present it, which is a good improvement because the last one last year was almost 200 slides. So I'm improving. What is the subject? What is the subject today? The subject is how to load kernel rootkits. And the part that I'm interested in is bypassing code signing, because now the kernel extensions must have a code signature, and bypassing the kernel extension interfaces. So I want to load rootkits in ways that are not supported directly by the operating system. This is going to be very useful because, for example, you can use these techniques to load a remote rootkit from the internet without ever touching the hard disk. So forensics will have problems to identify if there is a rootkit on disk or not. I also put there backdoors. This is a very loose definition of backdoors. In my opinion, they are backdoors because one of the vulnerabilities is known by Apple, and they didn't patch it. Then you have one feature that they implemented on the last version, Mavericks, but the way they implemented it's open to rootkits and everything. So for me, it's a backdoor in a loose way where you consider everything that you know or everything that is as a really bad implementation that you can abuse. And they also have a design and implementation flaw that I will show you first, which is also really bad, and I don't understand why they do this. Assumptions. If you read my bio, I am graduated in economics. Economists love assumptions, so let me show you what are the assumptions for this presentation. The presentation assumes that you have root access in macOS. All the techniques require root. They are not exploitable from a normal user. But my point is, what do you think is the probability of getting root in a Mac system? We can discuss this if you want. For me, anything below high, it's wrong. So it's very easy to get root in Mac systems. To prove my point, you have Google Project Zero. There's a single guy, Ian Beer. He has been working like half a year, or I don't know, and he published all these vulnerabilities. If you look with some attention, most of them are kernel code execution. And Google was interested in this to protect their browser, Chrome. So you can execute code from the browser. This says everything. You visit a website that is using one of these exploits, you get your computer directly owned by a rootkit, for example. So I think this makes a very strong point. More fun than this, you have that note from Google Project Zero, which says the bug, some vulnerabilities have been patched in iOS, but in macOS, nothing happens. So you have this problem where iOS is patched and Apple doesn't care about macOS. I cannot understand this. Google also published one exploit. This exploit, if you have been paying attention, this exploit works in Mavericks. The bug is patched in Yosemite, but all other versions are still vulnerable. And the exploit is very reliable. You execute it, it works, you get root, that's it. It's very stable. I only crashed this exploit once in so many attempts, so it's a very good exploit. I'm not sure why Google released this. More points. This is from a Korean researcher. He has been showing videos, demos about this. He has a remote code execution in Safari with local privilege escalation. So you go to a web page, and he gets remote code execution on your computer and can execute code as root. So basically, you visit that website, and your machine is dead. Or you can go the easier way. This worm wasn't the news a few months ago. It infected 17,000 Macs just by asking the user, please give me root. That's it. And there are more worms like this in Mac, where they just infect thousands of computers by asking the user, give me root. There are also more problems. You have installers, all kinds of installers, asking for root privileges. Please give me admin privileges because I need to install something. You have updates downloaded over HTTP without any authentication that ask for privileges. So the surface is big. So my assumption is it's not that difficult to get root on your Mac, and after that point, you can do whatever you want in the machine. So what I want is load kernel code, is my goal. Is this a problem? As I told you, Apple introduced code signing in the latest version in Mavericks. At the time, it wasn't a fatal error, so you get something like this. If you try to load the code, Mavericks will say, OK, this code is not signed, but I will load the code anyway. I have no problems with this. They did this basically because of a transition period. If they put this as, you must have this, it will be a confusion in everyone. In Yosemite, it was turned on by default. So if you try to load code that is not signed, Yosemite will not load that code. It will refuse it. It will refuse. It will say, it's not code signed, get out. So what are the consequences? You cannot load kernel code using the normal interfaces if it's not code signed. If it has an invalid code signature, meaning you can patch the binary, it will fail the code signature and can't work anymore. And you can't also use the Apple identifier. There was a trick, which is if you put your extensions with com.apple on the bundle identifier, you can load code very early in the machine. This is a backdoor that Apple uses, for example, to load the sandbox kernel extensions. But now they check. If the certificate is not from Apple, you cannot use this anymore. What are the solutions for this problem? You can steal or buy a code signing certificate. Stealing, Stuxnet did this. They stole 2 certificates from Chinese companies to code sign their malware. You can disable the code signing check by putting that boot parameter. Basically, you say, I want to put my machine insecure. I want to accept any code. Usually, people that use this mode is developers because they want to test all kinds of code. You can do EPI attacks. If you know the presentations from Snare, basically, you plug in a Thunderbolt adapter, and your computer can be hacked. So you are attacking the computer before the boot, so you can bypass any check. You can attack the userland daemons. This is the design flaw that I will show you. You can exploit kernel vulnerabilities. There's tons of them. And you can abuse some features. That is my last point to show you. Let me go through userland daemons. in macOS, you have this daemon, KXD, which is responsible for loading the kernel extensions. Basically, when you run the command to load the kernel extension, it sends a request to this daemon, and this daemon will process the kernel extension and ask the kernel load this kernel extension. It runs in ring tree. Basically, it's a daemon running in userland. It's not kernel code. And now it's responsible for code signature checks. So what you have a userland daemon checking the code that goes to root. This cannot work. Because you just need to find the place in the daemon where the check is made, you patch it, and you bypass the whole protections. It's easy as patching 2 bytes. You patch that call, or you just modify the return value to 0, and that's it. You can load any kernel code you want. You can also make this persistence by, instead of attacking this daemon, you attack the utility that generates the cache. Because in Mac, you have a kernel extension cache to make the boot fast. So you just modify once the cache. Unless there is an upgrade, you get persistency of your rootkit forever in the system. You don't need to bypass it anymore until the cache is updated. The funny stuff is that I wrote about this last year. It's not exactly this attack. At the time, it was just patching the message because the attack was made against Mavericks, and Mavericks would display a warning, this code signing, this kernel extension, it's not signed, be careful. You could just patch that message, and the user would never see that, so it's basically the same problem. You have code running in userland checking code that's going to a higher privilege ring. So this cannot work. This is a really big design flaw. Apple says, or said to me in private, this wasn't meant to be a security feature. Then my point is, if it's not meant to be a security feature, why are you implementing this? Okay, you might want to control code to kernel because you want to get rid of bad code, but at least tell people this is not a security feature. Apple doesn't has the really bad habit of not saying anything of what they do. They just implement, and that's your problem to guess what is this for. So I could end my presentation here because you just patch that and it's game over. But let's go to more fun stuff. I really like this cartoon because it shows you can have firewalls, AVs, next generation endpoint stuff, everything, but there's always Dave, the human. And the human will always make mistakes. And vulnerabilities will always be present. This is one of the reasons why I doubt about the presentation in the morning about disclosing all the bugs, because there will always be bugs. And you are always a 0 day away from being owned. So we need to think in a different way about these problems. What type of kernel vulnerabilities do we want? The best one is write anywhere. If you can have a vulnerability where you can write any bytes, any number of bytes you want anywhere in the kernel, it's the best one. There are two interesting points, which is the kernel task port and the host privilege port. This comes from the design of Mac system, which powers macOS. They are basically very powerful ports. If you control these ports, if you have access, you can do everything you want to the system. The reason for this is that the kernel is also a task in Mac. So you can think about this as the kernel as a process. So if it's a process and you got the task port, you can do everything, you can control the ports. Debuggers, for example, use the task port of every process to control the processes. So you get first the task port, and then you can control the process. This is the reason why debuggers need higher privileges in Mac. Before Snow Leopard, you could directly access the kernel port without any control besides being root. So you just use that function, task for PID 0, and you got the kernel task port and that's it. There's a description of this trick on that FRAC article where they talk about rootkits using this. I'm doing more or less the same, but updating the techniques for new protections in Mac. Let me skip this. This is the function. This year, 2 Taiwanese researchers presented a new vulnerability that gives you the same port. The vulnerability is in this function, processor set tasks. And the funny thing, it is that was also described on this book. If you know this book, macOS and OS Internals book, it describes the vulnerability. It doesn't say it is a vulnerability. When the 2 researchers presented this, it made a click on my mind. I saw this somewhere. I went to the book, oh, it's here. Funny stuff. It was there all the time, but I didn't look at it as a vulnerability. Gives you, as I told you, the same kernel task. This is the function, calls another function, and this is the funny detail. This is the function goes through all the tasks in the system and returns the ports of the task, including the kernel. The funny detail is that you have that defined, secure kernel. What is the secure kernel? It's the definition that Apple uses for iOS. So this is the proof that Apple knows about this bug. This bug is patched in iOS, but they leave it open in macOS. I don't know why. It's still not patched in Yosemite. The latest version is 10.10.1. I tried it, and it's still not patched. So it's every bit as vulnerable. They keep you vulnerable with bugs open. That define is the proof that Apple knows the bug, and more funny than this is that if you patch the bug yourself, you can do this with binary patching on your system, or you can compile the kernel yourself. There are no problems in patching this vulnerability. There is nothing that uses this feature. There's no program in your system that needs the kernel port, so I don't know why they don't patch this. For me, it's really strange, and this is one of the reasons why I call it a backdoor. So what we want, exploit this. How to exploit? We can, with this vulnerability, we can read and write any location of memory, kernel memory that is writable. We can allocate kernel memory with this vulnerability, and we can also read anything. One of the problems of this technique or this vulnerability is that we cannot change the memory protections of some places or some pieces of interesting parts on the kernel. We cannot modify the kernel codes directly, and we cannot modify some data sections that are made read-only. And we cannot execute code. We have control of the task port, but we have no way to start that code. This is what I want to show you, how to start the code. A brief overview on the kernel protections that you have now. The kernel code is made read-only. It's not, if it was normally a memory, you have a protection and you have somewhere in the system, what is the protection of that page on memory? But what they do is they modify directly the page protection. So even if you use a function to change the memory, you tell it, I want to make this memory writable, the system will not accept it. It will say, okay, yeah, I did it, but it will not change because it's, the change is at a lower level that the function cannot access. And the same is happening with that data sections. The reason for this is that if you know rootkits in Linux, it was one of the oldest techniques. You can modify the system call stable. You just modify a pointer, and you can then execute code. It's not possible anymore because the data where that table is located is made read-only. So it has the same thing. They protect, they make that memory non-executable. So you cannot execute code from there, and you cannot also write code there. It's possible to write those pages. You just need to disable the write protection bit in the CR0 register. This is also a known trick used by rootkits, both in Windows, Linux, and macOS. But the problem is that we need code execution. So we need first to execute code to disable the bit. Kernel ASLR was introduced in Mountain Lion, if I'm not wrong, or Lion. It's not a problem here because you have a function, the KAS info system call, that you can use it to get the slide. In iOS, this is not possible because they patch this function. It would be a big bug in iOS. It is the same bug in macOS. There's no real purpose to have this function. Or you can just use infoleaks. There's also tons of infoleaks, so you can use that to get the slide. So I want to execute kernel code. How to do it? As I told you, we cannot modify the kernel code. It would be easy if we could do it. We just need to modify hook some function and call that function. It would be easy. Or we cannot also use the syscalls. It would be the same thing. You just modify the pointer and you direct to your code, call the system call, and your code is executed. We cannot do that. You cannot also attack the kernel extensions. They will be a good target because if you look at the protections on disk, they are writable. The problem is that most of the time they are loaded from the kernel cache, which is the default, as I told you. And the kernel cache, Apple modifies the memory protection. And they are also not writable there, so you cannot use them for the same purpose. What is the solution? DCOM, direct kernel object manipulation. So the idea is you find some place that is writable, and that place will execute code. This means, for example, a function pointer somewhere, a pointer for a data structure that you can write. So the idea is you modify that pointer or that structure, and then you can execute a small shellcode, for example. A few bytes, you just need a few bytes to disable the CR0 protection. That's it. You disable, and then you can write to everything, to everywhere, and then you can fix everything else. Or you can just use that to load the rootkit code, the full rootkit code, and that's it. It depends on how much space you can find. What I'm going to show you is how to attack TrustedBSD. When I sent my slides to review for Stefan SR, he told me, oh, you keep abusing TrustedBSD. It is true. If you see my past presentations, I have been using TrustedBSD for everything. The main reason is that it's very stable to use TrustedBSD, and I have been working for this since forever, so I know it very well. TrustedBSD, what it is? It's a mandatory access control framework. It was started in FreeBSD. Then Apple ported it to macOS and to iOS. It is the basis of the sandbox because it allows you to control what the system is doing. And it's also used for gatekeeper and for code signing in iOS. In macOS, you don't have code signing, mandatory code signing userland, so it's not used there. You have many hooks available in the system. This is what allows you to control the system. Basically, you have a hook, and then that hook is called if a module is interested in controlling that function. So basically, you have many policy modules, how they are called, that they say, I want to listen to this function, and this function. And then they have some logic that says, okay, the function is authorized, the function is denied, and that's it. For example, code signing, when you try to execute something, it goes a request to a userland daemon. The userland daemon processes the signature and sends back the result to the kernel, and the kernel says yes or no, depending on the result. What is the funny stuff or the features that are great for us? The policies can be added or removed in a dynamic way. Because on boot, Apple modules are loaded, and then you can load additional modules on this. I have been fighting with Apple because Apple is closing this interface to developers. They are making this interface private. For me, it's a real shame they are doing this because this is a very powerful module that you can use to implement many features on your system and protect your systems. It contains writable data, and it leads to code execution because if it's a hook will call a pointer, and that pointer can be anything else that is executable. So you can abuse this for code execution. How? You just add a new policy, write a new policy to kernel memory with a single hook. We just need one hook to execute code. You modify that hook to point to your rootkit that is already loaded in memory, and then you call the function that triggers the hook, and your rootkit will start. How to do it? I resumed this to 10 steps. It's a bit more complicated. This solution is probably not the most elegant one or the most efficient one. It works. You can improve. You can do this in different ways. I'm just showing you a way to do it. The first step is to get the kernel port using that vulnerability. This is the code that you use. It's very simple. You just execute the function, and then you get the first element of the array, which is the kernel task. This is guaranteed to be this way, so you can hard code the element 0 on your code. Then you need to find the kernel ASLR slide. As I told you, this is very easy. You just need to use that syscall. You get the value, and you have the slide. You need to compute your rootkit size because you want to allocate memory where to load the rootkit. There is a small trick that you need to pay attention, which is you need to use the virtual memory field from the header of the rootkit. What you do is you process the rootkit itself, the header, and you go see what commands, what parts of data you need to load in memory. There are two fields in the header. One is the size on disk, and the other is the size in memory. They can be different because alignment spaces. Computers or the x86 architecture works better if memory is aligned. So usually the memory in programs is aligned, and if the size of the data on disk is smaller, then or bigger for a bit, if it's not aligned, then they put the memory aligned, then it will be different. So this is just a small trick. Then you need to allocate kernel memory. You can use this function, Mac VM allocate. The first parameter is the task where you want to allocate memory. So this can be used for attack or to patch or to allocate memory in any program. We just want to do that in the kernel. There is a parameter which is the flag, VM flags anywhere. It tells allocate memory anywhere. You can pass a parameter which says allocate memory on this specific location. The problem is that you don't know where to allocate, so you just want to allocate somewhere, and then you can use that memory for the rootkit. Then you need to copy the rootkit to memory. You also use another Mac function, Mac VM write. It takes the first parameter, the same task port. You copy each segment, and in this case, you use the file size. Because if you use the VM size, you run into problems of reading data outside the correct location. So you use the file size, and you don't care about the other contents because that's just alignment, and that's it. It will not be used for anything. Then you change the memory protections using another Mac function, Mac VM protect. You want to make the code executable because when you allocate new code, it's just readable and writable. It's not executable. So you need to change the memory protection. You can use the virtual memory size because you want to make also the alignment space executable in case there's one page difference, and it will lead you to a kernel panic. So use the VM size, make all the memory executable. Problems. The problem using the VM allocate is that the memory is not wired. By wired, it means the kernel will not put all the pages. You can copy the data, and the data will not be available, fully available in the kernel. So when you try to access this, it will kernel panic your system. This is not a problem if, for example, you just use a shell code, so one-page shell code, it will not be a problem. But it's a problem if you load directly a big rootkit in memory. So the result is a page fault, kernel panic. When you try to access, for example, more than 2 pages, in my experience, 3 or 4 pages, it will lead to kernel panic. The solution is to make that memory wired. Fortunately for us, there is a function. The MACVM wire can make this memory already wired, and that's it. The only trick for using this function is that first you need to make the protections that you need. So you make the memory first executable, and then you call this function. What the kernel will do, it will page in all the pages and make this memory wired, and no more problems with these kernel panics with page faults. So it's a very small trick, and it works without any problem. You also use you need to use the same protections. So on point 1, I have VM protect all, which is the same as on point number 2, where I described each item on the protection, but it's the same value. Another step, because we are loading directly the kernel code without using the kernel interfaces, there is no kernel linker to do the job of linking the symbols that we might use from the kernel. For example, if you want to use a printf for debugging, you need to do the linking. If you are just doing shell code without using any symbol, there's no problem. This is not a problem with the kernel code. You don't need to relocate this code. You don't need to, for example, fix offsets, because that code is position independent. So it will change where it is. So the code is relative to each other, the positions, but we need to fix the symbols. This is very easy than it seems. You can use the information on the relocation tables. This is what the kernel uses, the kernel linker uses, because it needs to know what must be fixed. This information is available on those 2 commands on the header. There are 10 different types of relocations in macOS. And you look at this, oh, there's too many, I need to make too much code, or you need to rip off the linker, the kernel linker code. But the advantage is that the kernel extensions only use 2 types, those 2 types. One is for relative addresses, where you use the offset and compute the difference, and another is for absolute addresses, which is where the code is. I made a small program to go over all the kernel extensions in the system, because I wanted to know how many types are used, and I can prove you that only those 2 types are used. This is how you do the processing of the tables. First, you'll read the relocation table. There's 1 entry per symbol. If the symbol is duplicate, it will still have 1 entry, because that entry says the symbol is used on this location, on that location, and that location. So you need 1 entry. Essentially, you process that table. You need to find where that symbol is in the kernel, because you need to find where is the target address where the symbol goes. And then you need to fix the symbol. To fix the symbol, the ones that are relative, you just need to compute the offset. This code has a problem because you can see an overflow on that code. I was just doing a proof of concept and left it like that, because if the offset must be 32 bits. If that offset is higher than 32 bits, then that value will overflow. The the offset will be wrong and you will have kernel panic the moment you use that symbol. But assuming the offset is okay, then you just need to write to the location that the relocation table tells you it's on this address, you put there the offset, and that's it. For the other type of symbols, the absolute ones, it's even easier. You know what is the full address, you just write the full address on the right location, and that's it. This is the processing of the local type of symbols. I will skip this over. It's more or less the same. There are local symbols and external symbols. The external symbols are the kernel ones, and the local are stuff like strings and some internal symbols on the kernel extension. So it's more or less the same process. You just need to fix it. To install TrustedB policy, I will have to go faster on this one. This is the layout of a TrustedBSD. There is a core structure, the MAC policy list, which tells you how many policies are loaded, and then it has a pointer, the MAC policy list element, which is the policies that are loaded in the system. That pointer is just a pointer to an array of MAC policy conf, and the MAC policy conf is the configuration for each policy that is loaded in the system. Basically, it contains information about the name, some flags, and the most important structure is the MAC policy hops. The MAC policy hops is a big structure that contains all the functions that are available in TrustedBSD, and it's there where you put a pointer. So if you want to listen to a hook on the system, when you load the system, you say, point this function to my function that will control, and that's it. So you don't need to listen to all the functions. You just put a pointer on the functions that you are interested in. This is how TrustedBSD implements the policies. There are 4 or 5 macros that some return false or not and different ways. Basically, all the functions go through the policies and check. If there is a valid pointer, call this pointer, and then your policy model gets control. So this is how you achieve code execution. If you have that pointer, and if TrustedBSD, when it's iterating over the policies, if it sees a valid pointer, it calls your code. So if you have a valid pointer to your rootkit starts. This is the policy conf. There's one small detail. I don't have it here. All the fields there, you can make them null. All the fields except the policy hops. You can configure them. You just need to allocate memory, for example, for the strings there. But it's really not needed. You just can simplify, make everything null, and just make a valid pointer to the MAC policy hops. So as I told you, it holds the hooks, and it's what we use to start the rootkit. These are the steps to install the TrustedB policy. We do it backwards because we don't want to install the policy and point somewhere. So first you allocate and install the policy hops, which tells you the pointer to your rootkit. Then you install the MAC policy conf. Then you add the policy conf to the entries, and then you activate this. How do you activate? You just add the number. If you check the macro will check the number of policies. So when you increase the number of loaded policies, then it's finally executed. Let me just go through something. So this is the MAC policy obstructor. There is one problem that you need to hard code this structure because it's not public, but it's stable. So you can select a pointer and you know that position is responding to that hook, and it will always be executed. So you can use any version of this structure and it will be okay. And this is the code that does that, nothing special. one thing that you need is to find the rootkit entry point, because you need to point where you want your code to start. You could hard code this value if you have a very specific rootkit and you can hard code. I don't like to hard code stuff. You can do it in a dynamic way. So basically, you process the rootkit header. You locate that symbol, the kmod info, that will tell you where the rootkit starts. This is the code. You get information from the header, and then you do this. You do a cast to that structure, the k-info structure, and you get the start address field. This will give you an offset, because the rootkits, the kernel extensions, don't have a fixed address because they will be loaded in different places. What you need to do is to find where the rootkit, where you allocated the base address of the allocated memory, add the offset, and you got the real address where the starting point is. So nothing very difficult. As I told you, you can put all the fields null. One thing that you don't need to worry is that the array where all the policy modules are, that array is pre-allocated. I think it's like 1,000 entries or something like that. On Mac, on a normal Mac, you have 4 modules, so there's enough space. You just need to find a free entry, and you put your entry there. So very, very simple. How to start the rootkit, assuming that we hook the task for PID. I select that function because it's easy to call, and very few other programs call this function. So you are not entering a race condition. You could use other hooks, but for example, you don't want to use a hook that is very used because you can enter race conditions between your kernel extension and others. So it's easier to use a function that is not used often. You need a PID to start this function. You can use the PID 1, which is for launchd. If you come from Linux, it's the same process as init. So it's guaranteed to exist always in the system, so use it. And then you can put, or you should put, a fuse in your rootkit code, which says when you start executing the first time, stop executing any further. Because the thing is, if some other function calls this function task for PID, the rootkit will be started again. So you don't want that to happen, most probably. So it's add a fuse to avoid any race condition on your rootkit. You still have a problem with race conditions. You could have two functions starting at the same time. This is one of the reasons for using a not used function or not very frequent function. It avoids these problems. And then after the rootkit start, you can do cleanup. You don't need a rootkit to start again, so you can go through the structures that you allocated and clean up, disable everything. You can wipe memory. You can start doing tricks with your rootkits and so on. You are just executing rootkit kernel code, so you can do everything you want at this time. Let me show you a demo. So this target system is Mavericks. I'm using Mavericks because I'm going to show you the Google exploit. I added the exploit to my payload. So I'm running as a normal user, non-privileged user. So let me execute this. And I'm going to execute a remote payload. So I can show you everything. So this is running the exploit to get the root privileges that I need to execute. And then it's doing its job of loading the kernel payload and everything else. And now, and this is what this rootkit does. It does nothing. It just prints a message. But here it is. This rootkit came from my website. It's located on my website. So it's a remote rootkit. It doesn't need to touch the disk because you just get the rootkit from the network into a buffer and then you upload to the kernel. You also don't need to, for example, to use my code directly from the disk. Assuming you have an exploit, you just download the code, you execute the code from memory, you get the payload from somewhere on the internet, and that's it. You can load a rootkit on the system without any touch on the disk. So as long as the user doesn't reboot, you got a rootkit loaded without any trace on the disk. So this is very, 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 very powerful. I can show you. Let me see if this works. If it doesn't, kernel panic. This is not a rootkit. This is one of my applications for anti-debugging. It fixes some stuff that some applications use for anti-debuggers tricks. So this is a more complex payload. Hopefully, it will not crash my system. It's loaded. And now let me use the control. This is a small utility to set the parameters that you want to use. And now let me load the debugger. So this small utility will contains anti-debugging protection. So if the debugger, if the anti-debugging is working, you get this error code, error 55. So now we just set the ptrace anti-debugging, we run again, and that's it. So it's working, a bit more complex kernel code is running stable without any problems, and this proves the point that you can easily load a rootkit, a fully working rootkit without any major problems. So it's really powerful, this small trick that you can use. Second vulnerability. This one is even more fun. I call it this guy's dev keymem. If you've come from Linux, you know that there is a device that allows you to access kernel memory. I'm not sure what is the status now. I think it's a bit more protected in Linux. I haven't worked with Linux in a couple of years. But this device existed in Linux. You could access directly the kernel memory by writing or reading from this device. This device exists in macOS. The question is that it's not enabled by default. Once again, you need to change the boot parameter to enable this. You just need to change the boot parameter on that file. You use the keymem equal to 1, and you reboot, and you get this device. I, for example, use this a lot for debugging. Sometimes I don't want to have a kernel debugger attached to my VM for testing. I just want to read some bits of memory. I have a small util that uses this, and I can read any kernel memory. Lately, I added a function to disassemble because sometimes I want to see if the code that I wrote is okay, so it disassembles everything using capstone and so on. In Mavericks, and let's get to the fun stuff, in Mavericks, Apple introduced this extension, Apple Hardware Access Kernel Extension. What this allows you is to read and write any bit of physical memory in your machine. There's a catch on any, because in real hardware, you have some hardware mapped in memory. So if you try to read those bits of memory, you get a machine check exception, and that will kernel panic your machine. But essentially, you can read and write kernel memory directly using this extension. It has another catch. You can read only up to 64 bits per request. So if you want to write like too many bytes, you need to send more requests. So it takes some time to do it, but it's feasible, and it's not a major problem. It's just more annoying on your code. So when I saw the first time I saw this bug, I didn't pay attention really to it. I was, okay, yeah, this is a feature, okay, it's interesting. And then I was developing the first technique, and I remember it made a click on my head. I can use that vulnerability because now I have the techniques, I have everything developed. I can use the other technique, or the other bug, or the other feature to load rootkits. It's a bit different, the technique, but the principle is more or less the same. This was found out by that user on that forum. He was the first person describing this. He posted a code snippet, how to read and how to write using this function. As I told you, at the first time I saw this, I didn't pay much attention. I think I thought, okay, this is important, but I was busy with something else, and it's one of those things that you notice, but your brain is not really paying attention to that. What is the reason why this kernel extension exists? I'm just speculating on this. I'm not sure if this. There was a feature on old macOS which is SHUD. SHUD is used for profiling, so you could use many tools, Apple tools, to profile your computer, for example, for performance and so on. They replaced that by that framework, Apple Profile Family Framework. And there's an interesting bit. They converted, it was initially a kernel extension, and now they moved that to a framework. So they moved from ring 0 to ring 3. So they still need to talk to the kernel because these functions are profiling the kernel, so they need. And they introduced this kernel extension. It's the only, that framework is the only code I can find in macOS system that uses this kernel extension. So I guess this is the purpose. Once again, Apple doesn't say anything about this, doesn't say what is the purpose. It sits there. It's loaded by default on your system. So you have a backdoor running on your system that can be abused. As I told you, we can read and write almost every single bit of memory, and we can bypass all the read protections because this function uses physical memory access, direct physical memory access. So we have access to all pages in your system, assuming you are not hitting a page allocated or paged on your hardware. The problems of this technique is that we cannot allocate memory because we are just reading and writing. We cannot change memory protections. I will show you why this might be a small problem, but we can bypass it. And we cannot execute code once again because we are just reading and writing memory. This is the function. This is how you call this. Essentially, this is an IOKit request. If you know IOKit, you just connect to the service. The kernel extension provides a service. You connect to that. If the connection is successful, now you can send requests. To send requests, you have two structures, the in and out structure. In the in request, the request that you want to read or write, you tell how many bytes you want to read or write. That value must be bits, so you need to multiply. You can read 1, 2, 4, and 8 bytes. And then you tell the address where you want to read. Then you call the function. You need to pass the parameter 0 for read, 1 for write. And if the call is successful, you will have the data contained on the out structure, where the kernel will put the data that you request to read. To write, it's more or less the same thing. You need to also put the size, the address you want to read, and you put the data that you want to write. So you just copy that to the structure. You send the request. If it was successful, then it is on kernel memory. How can we exploit this? We need more or less the same thing as the first vulnerability. We need to copy the rootkit to kernel memory. We need to fix the relocations. And we need to start the rootkit. The first two steps are easy. We can write to kernel memory so you can copy. To fix the relocations is also easy because it's the same technique. You can fix the relocations on userland, make it easier to avoid so many requests, or you can directly fix on the kernel. It's just a matter of personal taste. What are the problems? Memory allocation. What can you do to overcome this? You can find already allocated free space. There is a lot of free space in the kernel, for example, an alignment and so on. And the kernel header usually has a lot of space between the header and where the first code is located, so it's a good way. You can use the kernel extensions also. You can just patch a kernel function that is not used often. For example, NFS is a good candidate. I'm not sure who's still using NFS, but NFS functions are still in macOS kernel, so you have a lot of space there. Or you can allocate memory using shellcode. For that, you still need to find a small piece of memory to allocate the shellcode. I did that, the shellcode, without too many optimizations. It's like 200 bytes or less, so you don't need really a lot of space to solve this problem. The code execution, it's very easy to solve now because you can write anywhere you want, so you can patch the syscalls. You don't need to use the TrustedBSD or something complicated. You can use TrustedBSD if you are. You can hook a kernel function. You just hook the function, call the function, start your code, and then restart the function, and so on. You can hook a pointer. It's basically your creativity. The same 10 steps to victory. It's more or less the same stuff. You need to find the kernel KASLR slide. You need to find the available memory. This is just for avoiding you reading offsets, because if you go off the physical memory, you'll crash the machine. So you are just finding the upper limit, nothing too difficult. You need to find the kernel, where the kernel is located. As I told you, you can read almost every bit. The first time I was testing this, I was testing on a VM. Yes, it works because the VM doesn't have any hardware mapped in memory. And then I got into hardware and things start crashing. Oh, I know what it is, machine check exceptions, hardware mapped, so you cannot read the whole memory in a physical machine. Two solutions, the smart one, or not very smart, but I call it smart, and the brute force that can only work in VMs because of the kernel panic problem. The smart solution, it's very simple. You can read you know where the kernel is located. You read from the kernel image, then you have the kernel KASLR offset. This is one of the reasons why we need it. Then you just clear the highest 32 bits, and you get the physical location of the kernel page. This bug was also described by WinUCM for iOS. She tells where that iOS maps the kernel, and then if you do the same trick, you clear the bits, you get the physical page. The solution for this is to randomize where where the kernel is. It shouldn't be on the same page where the kernel memory is. This happens, for example, if you allocate memory. You can get memory in different pages, and you don't get the same guarantee that happens with the kernel. So this is a very easy trick to get the address. The brute force solution is just read everything. I will skip over this because of time constraints. Same thing, compute the rootkit size, the same exact technique for that. To find the free space. And the easiest way is to compute the free space between the header and the text sections. Usually is big enough for loading a rootkit. For example, it's big enough in Yosemite. You can put a full rootkit there. It's a few pages of alignment space. In Mavericks, you cannot do that. But you have like 2 or 3 pages enough, so you can use a shellcode for that. Well, it's just a warning, if you want to try the kernel extensions for this, it doesn't work because the headers of the kernel extensions aren't wired, aren't paged in, so you'll get the kernel panic, as I told you before. Another solution is to write the small shell code. You allocate memory. You find where you allocate that memory, and then you can upload the rootkit to that new area. Write rootkit to memory, just copy the same. It's the same thing as on the first technique. It just changes the way you write to kernel memory. To fix the rootkit symbols, it's exactly the same stuff. You just change the way you write. To find the rootkit entry point, same thing. You process the rootkit, you find the offset, and then you get where the rootkit will start. To find the system call table, I'm using the system call table on this one. What I do is you brute force, because you know where the kernel is, you can brute force the kernel space, and you can locate for known pointers that you know that will be located on the table. And then you can use, there are many system calls that are unused. You can use one of those to put your pointer and start the rootkit. How easy is it to find the system table? You know, there's an assumption. There are two functions, NOCs or NOCs, that are used to flag the system call. Basically, Apple uses this, so if anyone calls that system call, it returns an error. If it was, for example, a null pointer, you would crash the system. In Mavericks uses NOCs, and Yosemite uses NOCs. I have no idea why, but you can just hard code this or hard code another pointer, and that's it. After you find it, just update the pointer to your rootkit, and that's it. To start the rootkit, call the system call, and you get code execution. Quick overview, problems with this technique. The kernel header is not writable, as I told you. So, for example, you put a rootkit there. The rootkit has a global variable or some data that it needs to write kernel panic, because it cannot write it cannot write there. What is the solution? We cannot change the memory protection, or because of the page, but we can disable the CR0 protection, because we have code execution. So the first thing that we can execute on the rootkit is disable the white protection bit, and that's it. And then you can fix the rootkit. For example, you don't want to leave this bit disabled. What you want to do is copy the rootkit somewhere else, for example, restore the protection, clean the header, because that's really easy to spot. Look at the header. Hey, some code is there. This is very suspicious, but it's post-work. There is a problem. This register is per CPU core. Machines these days are multi-core, so you need to update the register in all the cores of the system. Because if you update only on the core that the rootkit starts, if another core calls a function of your rootkit, it will, and the white protection bit is set, then you run the risk of crashing the machine. So how can we run code in all the cores? Nemo published a long time ago in a FRAC article this function, MP rendezvous. What this function does, if you read the description, is guarantees to execute your code, your function, in every core of the system. This is what you want. You just put a small function that disables the bit, the write protection bit. Call this function, it sets all the cores. You are guaranteed to be safe on this. The function has some assumptions. You cannot use, for example, code that depends on locks and so on. But the code to disable the register is very simple. It is a few lines of assembly, so it's not a problem on this case. This is the example. The rootkit function, the start, is my entry point for the rootkit. I immediately call the function mpr and rendezvous that calls that function, disable all CR0. Then that function disable WP, it's very simple. It just sets, it's just an assembly stub that disables the CR0. So it's guaranteed before any other code of the rootkit is executed. all the cores have the write protect disabled, so no problems there. Let me show you quickly a demo. Like this, hopefully. So this is my physical machine. Let's go crazy. Hopefully it will not crash. Wow! Good thing it's a temporary password. So this is the same dumb rootkit, but not the remote version, because I'm not loading remote code on my physical machine. Oops. See, I have the service disabled on my machine because it's not needed for anything. Okay. So it's brute forcing the kernel, looking for the season table, and now executes everything. And as you can see, it's executed the code, the kernel. In this case, my example is loaded, is executing from the kernel, and that's it. It's game over. So quickly. Conclusions. After all this blah, 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 too long, what is the state of OSX security? This is my opinion. So take it with a grain of salt. Don't take it too seriously or take it too seriously. And don't tell anyone. Crap. Total crap. If you know The Simpsons, haha. Conclusions, very quickly. KX code signing is mostly useless. I will probably take out the mostly and put useless. Don't trust it as a security measure. This is very important. I like a lot human psychology, and people, or many people, will trust this as a security measure. Recently, like 2 weeks ago, there was an AV post writing something. Oh, don't worry. There is kernel extensions code signing in macOS. So this is a security feature. I hopefully have shown you that it's not a security feature. More important than this, Apple doesn't care about patching all vulnerabilities. I've shown you that they know that the first vulnerability, they don't patch in macOS. That vulnerability was presented at Black Hat, so it's not a small conference lost in the middle of nowhere. They saw the vulnerability, they know because they patch in iOS, and they keep the vulnerability open. I have no idea why. There is no official policy, end of life policy. For example, with Microsoft, Microsoft tells you, Windows XP on day X, no more security patches, and that's it. Apple doesn't tell you anything about this. It's either upgrade or just be vulnerable. Their assumption is a new version of macOS is released, everyone will upgrade the next day or in the same day. This doesn't make any sense. If you work, for example, in a corporate environment, it takes time. You don't have everything updated on the next day because tons of stuff can fail, and computers failing cost more money than security vulnerabilities, at least that is my opinion. And even if you upgrade, you are still vulnerable. As I've shown you with the first vulnerability, it's still there. Even on the latest versions, on the latest patch, it's still there. There's a blog post about this vulnerability. I wrote about it. I talked with Apple guys, Apple security guys. I don't understand it. So, Apple product strategy is reactive. They only react to what happens. Especially they react when you shame them in public, when you make them, okay, you are looking like fools. You can see these with iOS jailbreaks. The same vulnerabilities that were used on iOS 7 jailbreaks we're still working on iOS 8 jailbreaks with small modifications. So I don't understand this. Why not fixing bugs right away? And my question is if they have any strategy at all. The key point of this presentation, and to conclude, is if you have Macs in your companies, be careful. Everyone assumes they are not good targets. They are the best targets in your company because CEOs, CFOs, all the top guys love Macs because they are beautiful, and they are the best targets to attack because they contain good information. So be very careful. Check the assumptions. You don't have the same product, the product strategy that Microsoft has. Microsoft was in the same situation 10, 15 years ago. They improved a lot, and Apple needs to do this work. So be careful about that. I cannot disclose because I use a modified version. So this is my contact information. Feel free to annoy me, to ask me questions outside. Feel free to email me. I will happily help you with whatever I can. I don't know everything. The worst it can happen to you is me telling I don't know. I have no problem saying that. The first address is my blog. The second one is the GitHub where you can find all the code. I like to publish all the code. I'm not giving you right now the slides or the code. Because most probably I'm going to present at CSCAN, and I want to present there for some political reasons. But in March, you'll probably get the code. The code contains the Google exploit, so probably someone will use the code to do some malware. It's not my problem, it's Apple problem. They are the ones leaving you vulnerable, so blame them, not me. Yeah. Over.